Hi, I'm Tom, and this was Isambard Bristol's Durham Challenge. So we'll start with liquid on line 1, and we'll quickly look at the architecture. We've got 16 cores per socket, over 2 sockets, that's 32 cores, 64 logical threads, and we're on AMD. Other things to note are the cache sizes, and we might also think about the latency between different parts of the CPU, so the dies and the CCXs, and we know the CCXs have IF between them, Infinity Fabric, and that's almost as slow as between sockets. So let's get started. We'll load liquid by first loading the Intel compiler it's probably compiled with, and then we can start making some scripts. We've got 32 CPUs by task. It's on the CIUK dying petition, and we're hinting that we don't want any multi-threading. But more than that, we're also going to try and stop this with OpenMP. So we set up OpenMP correctly, and we're going to have 32 threads, not 64, because we're hyperthreading, and we're also going to select the number of regions to be correct to stop hyperthreading. And then we're ready to select our vector size and run the 5 liquid benchmarks that are available to us. And we get these outputs. We focus on triad here. It's 90,000. Tech power up quotes that its theoretical max for AMD EPYC 7302 is 204. We're not anywhere close to the suggested 400 then. Not yet. And we said we think hyperthreading would be bad, but we can try it anyway by changing the OpenMP threads to 64, changing the number region, and changing our run command. And this gives results that are almost exactly the same, which may be slightly surprising, but what's not surprising is the flops have dropped. And now on to Dyne 2 with liquid. Again, looking at the architecture, this Dyne 2 is an Intel processor. It has double the number of logical and hardware threads, or CPUs, and the number layout is different. It's even odd rather than sequential. It also has much larger cache. And we might also think about tiles and EMIB. So we can just load this again, change our slime script to be 64, and then we get these results. And the tech power up quoted amount was 281 per socket. If we look at the triad, we're at 200. So again, we're not really close, but much closer than we were on Dyne 1. And we can explain in a second. Notice that the flops don't have much change. So this is a brief overview of the comparison between them. We can see Dyne 2 is double in what seems to be the nodes and much more cache as well. So quickly looking at this, we see that some of the results for Dyne 1 are under 50%, some are just over 50%, and then we've got the peak flops on the other side is nowhere near 50%. Let's explain this. So EPYC might not have all its memory controllers saturated, and that's why it's less than 50. If a task is latency bound, then our interconnect will be slower than Intel's interconnect, which is EMIB versus IF. And perhaps the most important one, we can plug in an Intel compiler. And then quickly looking at the flops, why the flops greater than 50% here? There could be several reasons. The instructions per cycle are higher, or it might fit well into AVX2. Looking at stream now, stream is quite easy to compile. We can just run the default make file when we get it, and we get a trial result of 110. Again, we're not near to that theoretical max. Think about how we have valid stream runs. Amongst other rules, the important ones for us were making sure that we get the valid statement at the end of the run, that we didn't have a floating point error due to too aggressive optimizations. There needs to be a minimum of 10 runs, and that's done by default. And the problem size, the general rule for the problem size is 4 times the size of the sum of the last level caches, or 1 million elements, and we're much higher than 1 million elements. And our calculations for the min size are just above in green. So we might now think, okay, let's use an Intel compiler for Dyne 2, right? Because it's Intel. And so we load the Intel compiler and we set some flags. The ones to note are O3, which is aggressive optimization, and it might cause floating point error, but it didn't in our case. We use a valid array size, which is much bigger than our minimum. Shared Intel will use the shared libraries of the static ones on runtime. And then our final flag here is for non-pull streaming, so we don't pull large amounts, or do large array writes to the cache, if possible. And we could also try this Intel compiler on Dyne 1 as well. We set some AVX flags to help this, and then we run our command again. And then just some considerations for the Intel Sapphire Rapids, the architecture that this node is. Let's set the march to Sapphire Rapids in case it doesn't resolve correctly, and we'll also try X-Core AVX2 and AVX15, and we'll look at the results of those in a second. But first, back to Dyne 1. Now we've done an Intel-specific compiler, let's try an AMD-specific compiler. And this is a very simple script. The flags here, again, to note, are we using aggressive optimization, the most aggressive standard optimization? We're making sure we're using the correct march, and we want to use the MC modulus medium again, as we're expecting array sizes bigger than 2 kilobytes. And so now we can do our comparisons. So looking here, we've got 5 compiled codes, but we can only see 3. That's because in the green is overlapping the blue. That means there's no difference between AVX2 and AVX15, and they are much better than the AOCC for Dyne 2, and that's to be expected because it's Intel versus AMD CPUs on an Intel architecture. And again, the AMD lines overlapping on the bottom as well, and we can see what we expect really, that the AMD lines are much lower than the Intel, which had much more cores. The only other thing to note here is the shape, which we'll touch on later. And here we can just see a concrete example of which ones were better and worse. We see that AVX2 maybe had minimally more performance. This could be noise. The AMD compiler performed slightly worse, and then much worse than both of those, we've got the AOCC compiler and the Intel compiler on the AMD node. And note the Intel compiler is again quite good on AMD. Now describing this weird shape for AMD, AMD works by filling up CCXs, and so we can see when we are still in the same CCX, we're not seeing any, like a plateau basically, and then when we move into the next CCX, we see a little jump, and that's why we get this stepping pattern. And then for Intel with its unified memory architecture, instead of this filling up CCXs architecture, we have a much more smooth gradient. This is who we are, and thank you for watching. We'd like to leave you with our theoretical percentage of tech power ups quoted, which was 67% at most for Dyne 2 and 42% at most for Dyne 1, and our raw best scores, which were 370,000 for Dyne 2 and 172,000 for Dyne 1.